Physics stands at a peculiar crossroads right now, where decades of extraordinary success meet tantalizing hints that something profound remains hidden just beyond our current understanding. The standard model of particle physics, our most complete description of the fundamental building blocks of matter and the forces that govern them, has proven spectacularly accurate over the past 50 years. It predicted the existence of particles before they were discovered, explained phenomena that seemed mysterious, and tied together seemingly disparate aspects of nature into a coherent mathematical framework. Yet for all its triumphs, physicists have long known the standard model can't be the final word. It doesn't account for gravity, offers no explanation for dark matter or dark energy, and leaves fundamental questions about the universe unanswered. What makes this moment particularly exciting isn't just theoretical dissatisfaction with the standard model's incompleteness. Rather, we're seeing actual experimental results that don't quite match what the theory predicts. These aren't wild deviations that obviously signal something new, which in some ways would be easier to interpret. Instead, they're subtle discrepancies, small differences between measured values and theoretical predictions that hover tantalizingly in a zone of statistical significance where they might represent genuine discoveries or could evaporate with better data and improved calculations. This ambiguous territory is both frustrating and thrilling for physicists, because if these anomalies hold up, they could point toward new particles, new forces, or entirely new physics that operates beyond the standard model. Two experimental efforts have captured particular attention in recent years for their potential to crack open this door to new physics. The first involves measuring a property of muons called the magnetic moment with extraordinary precision. The second examines how particles called B-mesons decay in ways that seem to violate certain symmetries the standard model says should hold. Both experiments operate at the bleeding edge of what's technically possible, requiring incredible precision and years of careful work. Both have produced results that deviate from standard model predictions, and both have sparked intense debate about whether we're seeing the first glimpses of something genuinely new, or whether the discrepancies might disappear when theoretical calculations are refined. Muons are fascinating particles in their own right. They're essentially heavy cousins of electrons, carrying the same electric charge but weighing about 200 times more. This extra mass makes them unstable, living for only about 2/millionths of a second before decaying into other particles. Despite their fleeting existence, muons play outsized roles in physics. They rain down constantly from the upper atmosphere, created when cosmic rays collide with air molecules. They were among the first particles discovered in cosmic ray experiments in the 1930s, and they helped confirm one of the strangest predictions of special relativity, because muons created high in the atmosphere somehow reach the Earth's surface despite their short lifetimes, their internal clocks slowed by relativistic time dilation as they zip through the air at nearly the speed of light. Like all charged particles, muons behave as tiny magnets. This magnetic property comes from an intrinsic quantum mechanical characteristic called spin, though it's important to note that particles aren't actually spinning in the classical sense. The strength of a particle's magnetism relative to its spin is called its magnetic moment, and quantum mechanics lets us calculate what this should be for fundamental particles like electrons and muons. The simplest calculation gives what's called the Dirac value, but quantum field theory tells us the actual value should be slightly different due to quantum fluctuations. Here's where things get interesting. Even in empty space, quantum mechanics says the vacuum isn't truly empty, but instead constantly roils with virtual particles popping in and out of existence. These fleeting quantum fluctuations affect the magnetic moments of particles passing through this quantum foam. An electron or muon constantly emits and reabsorbs virtual photons, and these interactions shift the magnetic moment away from the simple Dirac value. The deviation is parameterized by a quantity called g, and specifically by how much g differs from 2, which is why physicists often talk about measuring g-2. For electrons, this g-2 value has been measured and calculated to extraordinary precision, reaching agreement between theory and experiment to better than 1 part in a trillion. This represents one of the most precise confirmations of quantum electrodynamics ever achieved, and stands as a testament to both experimental ingenuity and theoretical sophistication. The theoretical calculation involves summing contributions from virtual photons, but also from virtual particle-antiparticle pairs of every type that quantum mechanics allows. Virtual electrons and positrons contribute, as do virtual muons and even virtual quarks and W bosons and Higgs particles. Everything in the particle zoo contributes something to the final answer, though heavier particles contribute less because their greater mass makes them less likely to appear as virtual fluctuations. This is precisely what makes the muon G-2 measurement so powerful as a probe of new physics. The calculation includes contributions from every particle we know about, weighted by their properties. But if new particles exist that we haven't discovered yet, they too should contribute to the muon's magnetic moment through virtual quantum fluctuations. The muon's larger mass compared to the electron makes it more sensitive to these heavier virtual particles because the contribution of a virtual particle to G-2 grows with the square of the mass of the particle experiencing the quantum fluctuations. So while electron G-2 provides a precision test of quantum electrodynamics, muon G-2 offers a window into heavier physics, potentially sensitive to new particles even if they're too massive to create directly at current colliders. The quest to measure muon G-2 with sufficient precision has occupied physicists for decades. The most famous measurement came from an experiment at Brookhaven National Laboratory that ran from 1997 to 2001. The basic technique sounds almost simple, though its execution required extraordinary technical sophistication. Researchers created a beam of muons and injected them into a storage ring, a circular track held in a precise magnetic field. As the muons circulated around the ring, their spins precessed, meaning the direction their magnetic moments pointed slowly rotated, much like a spinning top wobbles. By measuring exactly how fast this precession occurred relative to the muon's orbital motion, physicists could determine the magnetic moment and calculate G-2. The Brookhaven experiment achieved remarkable precision, measuring the muon magnetic anomaly to about half a part per million. When they compared this result to the standard model prediction, they found a discrepancy. The measured value came out higher than the theoretical calculation predicted, differing by about 3 standard deviations. In the language of statistics, this meant there was roughly a 1 in 370 chance that random fluctuations could produce such a difference if the true values actually agreed. That's intriguing, but falls short of the 5 standard deviation threshold particle physicists typically require before claiming a discovery. For years, this Brookhaven result stood as a tantalizing hint that something beyond the standard model might be lurking in the quantum vacuum, contributing to the muon's magnetic moment in ways the theory didn't account for. Perhaps a new force mediated by an undiscovered particle was subtly affecting muons. Perhaps dark matter particles contributed to the quantum fluctuations. Perhaps supersymmetry, a theoretical framework that predicts a heavy partner particle for every known particle, was real, and its effects were showing up in precision measurements. The possibilities excited theorists, but the experimental situation remained ambiguous. A 3 standard deviation discrepancy is interesting but not definitive. More data was needed. Enter the muon G-2 experiment at Fermilab, which took up the challenge of measuring the muon magnetic moment with even greater precision. In a remarkable feat of experimental physics, the Fermilab team actually transported the storage ring magnet from Brookhaven to Illinois, moving the 50-foot diameter, 15-ton superconducting electromagnet 3,200 miles across the country. The journey included a dramatic trip by barge down the eastern seaboard, around Florida, and up the Mississippi River, followed by a careful overnight road trip through suburban streets to reach Fermilab. Once installed, the experiment began collecting data with improved techniques and higher statistical power than its predecessor. In April 2021, the Fermilab muon G-2 collaboration announced their first result, based on data collected in 2018. The measurement confirmed the earlier Brookhaven finding with even higher precision. The combined result from Brookhaven and Fermilab's first dataset showed a discrepancy with the standard model prediction of 4.2 standard deviations, strengthening the case that something genuinely anomalous might be happening. This announcement generated enormous excitement in the physics community and made headlines around the world. Could this be the long-sought evidence for physics beyond the standard model? But science is rarely straightforward, and the story took a surprising turn. The comparison between the experimental measurement and theory relied on theoretical calculations of the standard model prediction, and these calculations are extraordinarily complex. The most precise predictions used a technique that combines experimental data from electron-positron colliders with sophisticated theoretical modeling. However, an alternative approach using a method called lattice quantum chromodynamics had been under development for years. This technique uses powerful supercomputers to numerically solve the equations of quantum field theory on a discrete space-time grid, allowing calculations from first principles without relying on as much experimental input. In 2021, just before the Fermilab result was announced, a major lattice QCD calculation of the muon G-2 was published by the BMW collaboration. Their result shocked many physicists because it came out significantly different from the traditional calculation method, actually agreeing quite well with the experimental measurement. If the lattice calculation was correct, there was no discrepancy to explain. The tantalizing hint of new physics might simply reflect that the traditional calculation method wasn't as reliable as previously thought. This development transformed the muon G-2 situation from a clear experimental anomaly pointing toward new physics into a complex situation involving competing theoretical calculations. The traditional data-driven calculation suggested the experiments were seeing beyond standard model physics. The lattice calculation suggested everything was fine and no new physics was needed. Both approaches had strengths and potential weaknesses. The traditional method benefited from decades of refinement and cross-checking, but relied on experimental inputs that had their own uncertainties and assumptions. The lattice approach worked from first principles, but required careful treatment of systematic effects in the numerical calculations and enormous computational resources. The physics community finds itself in the somewhat unusual position of having an extremely precise experimental measurement while debating what the theory actually predicts. Several research groups are now working on independent lattice QCD calculations to either confirm or refute the BMW result. Meanwhile, the Fermilab experiment continues taking data, steadily reducing the experimental uncertainty. As of recent announcements, the combined experimental precision has improved, and the discrepancy with the traditional theoretical prediction has held steady at around 5.0 standard deviations based on subsequent data releases. This would typically be strong evidence for something new if we were confident in the theoretical prediction. But with the lattice calculation still being debated and refined, the situation remains genuinely uncertain. What makes this scientifically fascinating rather than merely frustrating is how it highlights the different kinds of precision required in modern physics. We've reached a point where experiments can measure quantities to parts per million or better, pushing the boundaries of what's technically possible. We can account for systematic effects, control backgrounds, and accumulate enough data to shrink statistical uncertainties to remarkable levels. But matching this experimental precision requires theoretical calculations of similar accuracy, and when you're computing quantum corrections that involve strong interactions between quarks and gluons, the math becomes extraordinarily difficult. You can't simply calculate these contributions using pencil and paper or even symbolic mathematics software. The strong force is, well, strong, meaning perturbative techniques that work beautifully for quantum electrodynamics breakdown. Non-perturbative approaches like lattice QCD offer a path forward but bring their own challenges and require immense computational power. The muon G-2 situation illustrates how discovery in modern physics isn't always a dramatic eureka moment. Sometimes it's a patient accumulation of evidence, a careful resolution of theoretical uncertainties, and a gradual consensus building as different approaches converge or diverge. If the discrepancy ultimately holds up and lattice calculations come into agreement with traditional methods while disagreeing with experiment, it would represent a major discovery, evidence for new particles or forces that lie beyond our current theoretical framework. If instead the lattice calculations are confirmed and the traditional approach was systematically overestimating the discrepancy, it would be a different kind of lesson about the importance of rigorous theoretical work and not declaring victory prematurely. Either outcome teaches us something important about how science works at the frontiers of knowledge. While the muon G-2 experiment measures a property of a single type of particle with extraordinary precision, another experimental program probes standard model predictions by studying the decay patterns of composite particles called B-mesons. These particles contain a bottom quark paired with another quark, and they're produced copiously in certain particle collider experiments. B mesons are unstable, decaying within picoseconds through processes mediated by the weak nuclear force. The Standard Model makes specific predictions about how often different decay modes should occur and how the products of those decays should be distributed, and any deviation from these predictions might signal new physics. Several experimental facilities have dedicated themselves to studying B meson physics with high precision. The Bell experiment at KEK in Japan and the Barbar experiment at SLAC in California were purpose-built to study B mesons and confirmed important predictions of the Standard Model, including subtle matter-antimatter asymmetries that helped explain why the universe contains more matter than antimatter. More recently, the LHCb experiment at CERN's Large Hadron Collider has taken up the mantle, collecting enormous samples of B meson decays and measuring their properties with increasing precision. The Standard Model structure imposes certain constraints on how particles decay, particularly through symmetries and conservation laws. One important principle involves what physicists call lepton universality. The Standard Model treats the three charged leptons, electrons, muons, and tau particles, as essentially identical copies of each other, differing only in mass. The weak force couples to them with equal strength. This means that when a B meson decays through processes involving the weak force, it shouldn't prefer to produce muons over electrons or vice versa, except for effects that arise purely from the mass difference. Since the particles involved in B meson decays are much heavier than electrons or muons, these mass effects are small, and lepton universality predicts that certain ratios of decay rates should be very close to 1. Measurements of these ratios have produced some of the most intriguing hints of potential new physics in recent years. Multiple experiments have observed that B mesons seem to decay to final states containing electrons more often than expected, compared to final states containing muons. The deviations are individually not overwhelmingly significant, but they appear consistently across different decay modes and different experiments. The combined statistical significance reaches the level where it becomes difficult to dismiss as mere statistical fluctuation, yet still falls short of the threshold for a definitive discovery claim. What could explain such a pattern? If confirmed, lepton universality violation would be profound because it would mean the weak force doesn't actually treat different lepton types equally. This could happen if a new force or new particles existed that coupled differently to electrons and muons. Various theoretical models have been proposed, often involving particles called leptoquarks that can connect quarks and leptons in ways not present in the Standard Model, or new heavy force carriers called Z-prime bosons. These hypothetical particles could contribute to B meson decays and alter the rates in ways that violate lepton universality. The experimental situation with B meson anomalies resembles the muon G-2 case in that we're looking at small discrepancies that persist across multiple measurements, but haven't yet reached the gold standard of statistical significance that would constitute an unambiguous discovery. The LHCb experiment has been at the forefront of these measurements, analyzing hundreds of millions of B meson decays to tease out the subtle patterns. Their measurements of quantities labeled Rk and Rk star, which represent ratios of decay rates to final states with muons versus electrons, have consistently come out lower than the Standard Model prediction of 1 by amounts that range from 2 to 3 standard deviations depending on the specific measurement and kinematic region. Adding to the intrigue, other measurements in the B meson system also show tensions with Standard Model predictions. Observations of how B mesons decay to specific combinations of particles called K-star mesons and muon-antimuon pairs show angular distributions that don't quite match theoretical expectations. The measured values of quantities with names like P5' show consistent patterns of deviation across energy ranges. None of these represents a smoking gun on its own, but taken together, they paint a picture that has many physicists wondering whether they're seeing the early signs of a coherent pattern pointing toward new physics. However, just as with muon G-2, there's an important caveat involving theoretical calculations. Predicting B meson decay rates requires understanding not just the weak force interactions that drive the decay, but also the strong force effects that govern how quarks are bound together inside the B meson and the particles it decays into. These strong interaction effects are notoriously difficult to calculate precisely, involving the same kind of quantum chromodynamics complications that plague the muon G-2 calculation. Physicists have developed various techniques to estimate these contributions, but uncertainties remain, and there's ongoing work to refine the theoretical predictions using lattice QCD and other advanced methods. This raises the possibility that some of the observed tensions might partially reflect underestimated theoretical uncertainties rather than genuine new physics. The community is working hard to resolve this question, with different groups tackling the calculations using different approaches and comparing results. Recent lattice QCD calculations of certain form factors relevant to B-meson decays have helped clarify some aspects of the theoretical predictions, while highlighting others that need more work. It's a complex landscape where experimentalists, phenomenologists, and lattice theorists must work together to separate signal from noise and robust predictions from speculative calculations. What makes the B physics anomalies particularly compelling to many physicists is that they seem to fit together into a potential pattern. If you hypothesize the existence of certain types of new particles with specific properties, you can potentially explain multiple anomalies at once. Models involving leptoquarks or new heavy-gauge bosons can be constructed that simultaneously address the lepton universality violation, the angular distribution anomalies, and even potentially the muon G-2 discrepancy. The fact that a single theoretical framework might explain multiple independent observations is suggestive, though physicists are cautious not to over-interpret preliminary evidence. The history of particle physics includes numerous cases where initial hints of new physics evaporated with more data or better understanding of detector effects and backgrounds. It also includes cases where persistent small deviations eventually built into confirmed discoveries. The Higgs boson discovery in 2012 followed years of increasingly strong but not quite definitive hints. The discovery of neutrino oscillations came after decades of measurements showing deficits in certain types of neutrinos that were initially controversial but ultimately confirmed a phenomenon not present in the original standard model formulation. The process of confirming whether an anomaly represents genuine new physics rather than an artifact of measurement or calculation requires extraordinary patience and methodological rigor. When the muon G2 experiment at Fermilab reported its results in April 2021, showing that muons wobble slightly more than predicted by the standard model, the physics community didn't rush to declare victory over established theory. Instead, researchers understood this as one important data point in an ongoing investigation that would require multiple independent confirmations and refinements in both experimental technique and theoretical calculation before any firm conclusions could be drawn. The experimental measurement itself represents a triumph of precision. The muons in the muon G2 experiment travel around a ring just over 14 meters in diameter, held in their circular path by superconducting magnets that create an extraordinarily uniform magnetic field. These muons, produced by smashing protons into a target and selecting the resulting muons that emerge, survive only microseconds before decaying into electrons and neutrinos. During their brief existence, the muons spin like tops, and their spin axis precesses or wobbles around the direction of the magnetic field. The rate of this precession depends on the magnetic moment of the muon, and any deviation from the theoretical prediction would indicate the presence of virtual particles popping in and out of existence around the muon, temporarily affecting its properties. Measuring this precession rate requires detecting the electrons that emerge when muons decay. These electrons are preferentially emitted in the direction the muon's spin is pointing at the moment of decay, so by tracking how the pattern of electron detections varies over time, experimenters can reconstruct the precession rate with astonishing accuracy. The precision achieved corresponds to measuring the diameter of a human hair from across a football field. Achieving this precision demands meticulous attention to details like the exact strength and uniformity of the magnetic field, the timing calibration of detectors, and corrections for various systematic effects that could bias the result. Yet even with this experimental precision, the significance of the muon G2 result hinges critically on equally precise theoretical calculations. This is where matters become particularly intricate, because calculating the standard model prediction for the muon's magnetic moment requires accounting for all possible virtual particle interactions that could affect it. Some contributions are straightforward to calculate using established techniques. The electron contributes in a well-understood way. The heavier tau lepton makes a smaller contribution. Virtual photons, W bosons, and Z bosons all play roles that can be computed with confidence. The difficulty arises when accounting for contributions from quarks and gluons, the constituents of protons and neutrons. These particles interact through the strong nuclear force, described by quantum chromodynamics, which at low energies becomes so complex that direct calculation from first principles becomes computationally intractable. Quarks and gluons can bind together into short-lived composite particles that briefly appear as virtual particles around the muon before vanishing. Calculating the contribution of these processes accurately has been one of the major challenges in determining the standard model prediction for the muon's magnetic moment. Traditionally, physicists have addressed this challenge by using experimental data rather than pure calculation, measurements of how electrons and positrons annihilate into hadrons, composite particles made of quarks. At various energies provide information that can be mathematically transformed into the needed contribution to the muon's magnetic moment. This approach, called the data-driven method, has been refined over decades and incorporates measurements from numerous experiments around the world. The most precise implementations of this method yield a standard model prediction that differs from the experimental measurement by about 4.2 standard deviations, a discrepancy that, if genuine, would be tremendously exciting. However, an alternative approach using supercomputer simulations of quantum chromodynamics has recently produced results that cast this discrepancy into question. In this lattice QCD approach, physicists divide spacetime into a discrete grid of points and use powerful computers to calculate how quarks and gluons behave on this lattice. This method has become increasingly sophisticated and accurate as computational power has grown and as theorists have developed better algorithms. In 2021, the BMW collaboration published results from lattice QCD calculations that agreed with the experimental measurement rather than with the data-driven theoretical prediction. If this lattice result is correct, the apparent anomaly would largely disappear, and the muon G2 experiment would simply be confirming the standard model rather than revealing cracks in its foundation. This situation highlights a fascinating aspect of modern particle physics. The uncertainty isn't primarily in the experimental measurement, which has been replicated at both Brookhaven and Fermilab with consistent results. Instead, the uncertainty lies in the theoretical prediction, where two sophisticated approaches using different methodologies yield different answers. Resolving this tension requires both improving the lattice QCD calculations and scrutinizing the data-driven approach for potential issues. Multiple research groups are now working on independent lattice calculations to verify or refute the BMW result, while others are examining whether the experimental data used in the data-driven approach might contain unrecognized systematic errors. The debate over theoretical calculations isn't unique to the muon G2 experiment. Similar issues arise in interpreting anomalies in B meson decays. The standard model makes specific predictions about how B meson should decay into various final states, but these predictions depend on understanding the internal structure of the B meson and how the quarks inside it behave. The calculations involve form factors, mathematical functions that describe how quarks transition between different bound states. These form factors can be estimated using various theoretical approaches, including heavy quark, effective theory, QCD sum rules, and lattice QCD, but each method has its own uncertainties and limitations. When experimental measurements of B meson decays show tensions with standard model predictions, as has been observed in certain angular distributions and branching ratios, determining whether these tensions represent genuine new physics requires confident knowledge of these form factors. If the theoretical predictions are even slightly off due to underestimated uncertainties in the form factors, what appears to be a significant deviation could actually be consistent with the standard model. Conversely, overly conservative estimates of theoretical uncertainties might mask genuine signs of new physics by making the predictions so broad that they accommodate a wide range of experimental results. Recent years have seen considerable effort directed toward improving these theoretical predictions. The lattice QCD approach has made significant strides, with increasing computational resources and refined techniques allowing for more accurate calculations of form factors and other hadronic quantities. Yet lattice calculations have their own challenges. The lattice spacing must be small enough to capture the relevant physics accurately, but making the spacing smaller dramatically increases computational cost. The volume of the lattice must be large enough to avoid finite size effects, where the boundaries of the simulated region artificially affect the results. The masses of the quarks must be carefully tuned to their physical values, which requires extensive calibration. And extracting physical quantities from the lattice results requires sophisticated statistical analysis and extrapolation procedures. Despite these challenges, lattice QCD has matured into a powerful tool for testing the Standard Model. Calculations of quantities like the proton mass, the masses of various hadrons, and the decay constants of mesons have reached impressive accuracy and agreement with experimental measurements. This success gives confidence that lattice methods, when properly applied, can provide reliable predictions. However, the calculations relevant to interpreting potential anomalies, such as the hadronic vacuum polarization contribution to the muon magnetic moment or the form factors governing rare B decays, push the limits of what current lattice QCD can achieve reliably. The interplay between experiment and theory in addressing these anomalies exemplifies how science progresses in areas where measurements approach extraordinary precision. Neither experiment nor theory alone suffices. The experimental results, no matter how precisely measured, require theoretical context to interpret their significance. The theoretical predictions, no matter how carefully calculated, must be tested against experimental reality. Progress comes from the dialogue between these two approaches, with each refinement in measurement driving improvements in calculation, and each advance in theory motivating more precise experiments. This dialogue has led to some surprises. In 2022, the CDF collaboration at Fermilab announced a new measurement of the W boson mass that differed from the Standard Model prediction by 7 standard deviations, if confirmed, one of the most significant deviations from the Standard Model ever observed. The W boson, discovered in 1983, is one of the carriers of the weak nuclear force and plays a central role in processes like radioactive beta decay. Its mass is related by the structure of the Standard Model to other fundamental quantities like the Higgs boson mass and the fine structure constant. The CDF measurement, based on data collected over many years at the Large Hadron Collider before it shut down in 2011, suggested a W boson mass about 85 million electron volts higher than the Standard Model prediction, a substantial discrepancy for such a well-established particle. If this measurement were correct, it would require either modifications to the Standard Model or contributions from unknown particles that affect the W boson mass through quantum corrections. The results sparked intense discussion and scrutiny. Other measurements of the W boson mass from different experiments, including results from the LEP collider at CERN and from the ATLAS experiment at the LHC, didn't show such a large deviation, though their uncertainties were generally larger than the CDF measurement. Understanding whether the CDF result represents a genuine problem with the Standard Model or an underestimated systematic uncertainty in the measurement requires careful examination of the analysis methodology. Measuring the W boson mass at a hadron collider like the Tevatron involves reconstructing W bosons from their decay products, typically an electron or muon plus a neutrino. Since neutrinos escape detection, only the charged lepton can be directly observed. The W boson's transverse mass, reconstructed from the charged lepton and the missing energy attributed to the neutrino, provides information about the W mass, but extracting a precise value requires detailed modeling of how W bosons are produced and how they decay, how particles propagate through the detector, and how various backgrounds contribute. Small uncertainties in any of these aspects could shift the measured W mass. The Parton distribution functions that describe the internal structure of protons, for instance, affect how W bosons are produced and could influence the reconstructed mass. The modeling of the detector response to electrons and muons, including energy scale calibration and resolution effects, directly impacts the measured lepton kinematics. The treatment of radiative corrections, where additional photons are emitted during the W boson production or decay, changes the expected distributions. Each of these effects must be carefully simulated and controlled, and it's possible that some subtle issue in the CDF analysis led to a bias in the result. Other experiments are now working to provide independent measurements with comparable or better precision. The LHC experiments, particularly ATLAS, CMS, and LHCb, are analyzing their data to extract W boson mass measurements. The larger datasets available from the LHC's high luminosity, combined with advances in analysis techniques and theoretical understanding, may clarify whether the CDF result is correct or whether it reflects some analysis artifact. Until independent confirmation or refutation comes, the particle physics community treats the CDFW mass measurement as an interesting hint that requires further investigation rather than an established challenge to the standard model. This cautious approach reflects hard-won wisdom from past experiences. The history of particle physics includes several instances where exciting deviations from expectations eventually turned out to be experimental or theoretical errors. In 2011, the OPERA experiment reported measurements suggesting neutrinos traveling faster than light, a result that, if true, would have overturned fundamental principles of special relativity. The finding generated enormous attention and skepticism, and after intensive investigation, the anomaly was traced to a faulty connection in the timing system and an incorrectly calibrated oscillator. The episode reinforced the importance of independent verification and thorough systematic checks before accepting revolutionary claims. Yet the cautious approach must be balanced against the need to pursue promising hints that might lead to breakthrough discoveries. If physicists dismissed every anomaly as likely to be an error, they might miss genuine discoveries. The art lies in maintaining appropriate skepticism while energetically investigating potential deviations to determine their nature. This means designing follow-up experiments, refining measurements, improving calculations, and exploring alternative explanations for observed patterns. The Bell 2 experiment at KEK in Japan represents exactly this kind of follow-up effort. Building on the success of the original Bell experiment, which made crucial contributions to understanding CP violation in B meson decays, Bell 2 aims to collect 50 times more data than its predecessor. This enormous dataset will enable much more precise measurements of rare decay processes and subtle asymmetries. If the tensions observed in earlier B physics measurements represent real deviations from the standard model, Bell 2 should see them with overwhelming statistical significance. If instead those tensions were statistical fluctuations or artifacts of smaller datasets, Bell 2's results should converge with standard model predictions as uncertainties shrink. Similarly, future muon experiments aim to further improve precision. The muon G2 experiment at Fermilab continues taking data to reduce statistical uncertainties. While a completely different experimental approach using a different technique is being pursued at J-Park in Japan. The J-Park muon G2 experiment stores muons at low energy in a compact magnetic field and uses different systematic controls. If both experiments ultimately agree on a value that differs from the standard model, confidence in the anomaly would increase substantially. Meanwhile, theorists continue working to resolve the tension between different calculation methods, with multiple collaborations pursuing independent lattice QCD calculations and others revisiting the data-driven approach to ensure all experimental inputs are properly incorporated. Beyond these specific anomalies, broader experimental programs continue mapping the landscape of particle physics with increasing precision. The LHC experiments are conducting comprehensive studies of Higgs boson properties, measuring how it couples to different particles and searching for any deviations from standard model predictions. These measurements probe whether the Higgs boson is exactly as the standard model predicts, or whether it has additional properties that would indicate extensions to the theory. So far, the Higgs behaves remarkably consistently with expectations, but uncertainties are still large enough that substantial deviations could be lurking just below current sensitivity. Searches for extremely rare processes continue pushing into previously unexplored territory. Neutrinoless double beta decay, a process that would violate lepton number conservation if it occurs, is sought in massive underground detectors shielded from cosmic ray backgrounds. Observing this process would demonstrate that neutrinos are their own antiparticles and would provide crucial information about neutrino masses and the matter-antimatter asymmetry of the universe. Experiments using tons of isotopes like xenon or germanium sit deep underground in mines or laboratories carved from mountains, waiting to detect the characteristic energy signature of neutrinoless double beta decay. After decades of searching with increasingly sensitive detectors, no confirmed signal has emerged, but the search continues with each new generation of experiments pushing the sensitivity further. Searches for proton decay similarly probe whether the apparent stability of ordinary matter is truly absolute or merely extremely long-lived. Grand unified theories that attempt to unify the strong, weak, and electromagnetic forces predict that protons should eventually decay, though with lifetimes exceeding 10 to the power of 30 years, far longer than the age of the universe. Detecting even a single proton decay would be revolutionary, confirming that the separate forces of nature are aspects of a deeper, unified force. Enormous underground detectors containing thousands of tons of ultra-pure water or other materials watch for the telltale flash of light that would signal a proton's demise. Despite decades of operation, no convincing proton decay events have been observed, pushing the lower limit on the proton lifetime to extraordinary values, but not yet ruling out all theoretical predictions. The search for dark matter, the mysterious substance that comprises most of the matter in the universe but doesn't emit or absorb light, employs multiple complementary strategies. Direct detection experiments deep underground use ultra-sensitive detectors to watch for the rare occasions when a dark matter particle might scatter off an atomic nucleus. These experiments must contend with incredibly low signal rates and must discriminate genuine dark matter interactions from various backgrounds caused by radioactive contamination, cosmic rays, and even neutrinos from the sun. Despite heroic experimental efforts achieving sensitivities to interactions billions of times weaker than the weak nuclear force, no conclusive dark matter detection has been made through direct detection. Indirect searches look for the products of dark matter particles annihilating or decaying in regions of high dark matter density, like the galactic center or nearby dwarf galaxies. Gamma-ray telescopes, neutrino detectors, and cosmic ray experiments search for unusual excesses that might signal dark matter interactions. Some tantalizing hints have appeared in cosmic ray data, including an excess of positrons at high energies and an unexplained feature in the gamma-ray spectrum from the galactic center. But alternative astrophysical explanations exist for these observations, and the jury remains out on whether any represent genuine dark matter signals. The LHC experiments themselves search extensively for dark matter by looking for events where known particles are produced in association with significant missing energy that could indicate dark matter particles escaping detection. These searches probe whether dark matter particles might be produced in high-energy collisions, and if so, how they interact with ordinary matter. Many specific theoretical models predicting dark matter particles with particular properties have been tested and excluded by LHC data, narrowing the range of possibilities, but not yet identifying the dark matter particle if it exists. The possibility that dark matter might not consist of particles at all, but instead represent a modification of gravitational physics on large scales, continues to be explored through both theoretical work and observational astronomy. Modified Newtonian dynamics and its relativistic extensions attempt to explain galactic rotation curves and other phenomena attributed to dark matter without invoking invisible matter, instead proposing that gravity behaves differently than Einstein's general relativity predicts under certain conditions. These alternative theories face significant challenges in explaining all observations that dark matter explains successfully, particularly the detailed structure of the cosmic microwave background and the behavior of colliding galaxy clusters. But they represent a legitimate alternative hypothesis that must be tested against observational evidence. The nature of dark energy, the mysterious component driving the accelerating expansion of the universe, remains even more enigmatic than dark matter. While dark matter's gravitational effects are well mapped through observations of galaxy motions, gravitational lensing, and cosmic structure formation, dark energy reveals itself primarily through its effect on cosmic expansion. Whether dark energy represents a cosmological constant, an intrinsic energy density of empty space that Einstein introduced and later regretted, or something more dynamic that evolves over cosmic history, remains unclear. Observations of distant supernovae, the cosmic microwave background, and the large-scale structure of the universe all point toward dark energy's existence and constrain its properties, but these observations leave room for various theoretical interpretations. The connection between dark energy and particle physics runs deep because quantum field theory predicts that empty space should have an energy density arising from quantum fluctuations. However, naive calculations of this vacuum energy produce values roughly 120 orders of magnitude larger than the observed dark energy density, an embarrassingly enormous discrepancy sometimes called the worst prediction in physics. Understanding why the vacuum energy is so much smaller than theoretical expectations is one of the great unsolved problems in fundamental physics, possibly requiring new principles or symmetries to explain. Some theorists suggest anthropic reasoning, arguing that only universes with small vacuum energy can form galaxies and stars necessary for life, and we naturally find ourselves in such a universe. Others propose dynamical mechanisms that might relax the vacuum energy to small values, or screening mechanisms that might hide its gravitational effects. Neutrino physics continues offering windows into physics beyond the Standard Model. The discovery that neutrinos oscillate, changing from one type to another as they travel, established that neutrinos have mass, something not accommodated in the original Standard Model formulation. The precise pattern of neutrino mixing, described by parameters analogous to the CKM matrix for quarks, is being measured with increasing accuracy by a global program of neutrino experiments. Some parameters are now known quite precisely, while others, particularly those involving the third neutrino type, remain less well determined. A crucial unknown in neutrino physics is the ordering of neutrino mass states. Two possibilities exist: normal ordering, where the third mass state is heavier than the first two, or inverted ordering, where the third state is lighter. Current data slightly favor normal ordering but don't yet conclusively determine which is correct. The next generation of neutrino experiments aims to definitively establish the mass ordering and to measure the remaining unknown mixing parameters with high precision. These measurements will guide theoretical efforts to understand why neutrino masses are so much smaller than other particle masses, and whether neutrinos gain mass through the same Higgs mechanism that gives mass to quarks and leptons, or through some alternative mechanism. The possibility that neutrinos are Majorana particles, identical to their own antiparticles, remains open and would have profound implications. Majorana neutrinos would allow new types of interactions that violate lepton number conservation and might explain the observed matter-antimatter asymmetry of the universe through a mechanism called leptogenesis. In this scenario, heavy right-handed neutrinos present in the early universe decayed asymmetrically into leptons and antileptons, creating a lepton asymmetry that was then converted into a baryon asymmetry through processes predicted by the Standard Model. This mechanism provides an elegant explanation for why the universe contains matter but virtually no antimatter, but it requires neutrinos to be Majorana particles, and requires the existence of very heavy right-handed neutrinos that haven't been directly observed. Searches for charged lepton flavor violation, such as a muon decaying into an electron and a photon, probe another frontier where the Standard Model might break down. In the Standard Model with massive neutrinos, such processes can occur but are suppressed to completely unobservable rates. However, many extensions of the Standard Model predict charged lepton flavor violation at levels that might be detectable. The mu2e experiment at Fermilab will search for muons converting into electrons in the field of an atomic nucleus, a process related to muon to electron photon decay but potentially more sensitive. If observed, charged lepton flavor violation would be unambiguous evidence for physics beyond the Standard Model and would provide crucial clues about what that new physics might be. The quest to understand particle physics at the deepest level increasingly points toward the need for new theoretical frameworks that transcend the Standard Model. String theory, which proposes that fundamental particles are tiny vibrating strings rather than point-like objects, offers one approach to unifying all forces, including gravity. String theory requires extra dimensions of space beyond the familiar three, with these extra dimensions curled up so small they're imperceptible at accessible energies. The theory makes few definite predictions that current experiments can test, but it provides a mathematically consistent framework that might describe nature at the most fundamental level. Critics note that string theory's lack of testable predictions and the vast landscape of possible vacuum states make it difficult to falsify and question whether it truly constitutes a scientific theory in the traditional sense. Loop quantum gravity takes a different approach, attempting to quantize general relativity directly without requiring extra dimensions or supersymmetry. This approach treats space-time itself as granular at the Planck scale, with discrete quanta of space and time replacing the continuous space-time of classical physics. Loop quantum gravity has made progress on problems like the physics of black holes and the Big Bang singularity, but connecting these insights to testable predictions remains challenging. The theory currently lacks a clear path to reproducing the standard model of particle physics, though research continues on this front. Other approaches like asymptotic safety, causal set theory, and various models of quantum gravity each offer different perspectives on how space-time and quantum mechanics might ultimately be reconciled. The diversity of approaches reflects both the difficulty of the problem and the lack of experimental guidance. Without data from energies near the Planck scale, where quantum gravity effects should become important, theorists must rely on mathematical consistency, elegance, and indirect connections to lower energy physics to guide their work. Yet even if quantum gravity remains experimentally inaccessible for the foreseeable future, the anomalies being pursued at current facilities might provide crucial hints about the path forward. If the muon G2 anomaly is confirmed and its source identified, if the B physics tensions point towards specific new particles or interactions, if the W boson mass truly differs from standard model predictions, these discoveries would constrain possible extensions to the standard model and potentially point toward the deeper theory underlying observed phenomena. Even negative results, definitively establishing that the standard model works perfectly up to some energy scale, would be valuable by ruling out various speculative extensions and narrowing the search space for new physics. The sociology of particle physics shapes how these investigations proceed. Large collaborations involving hundreds or thousands of physicists work together on experiments that require decades from initial conception to final results. Decision-making about detector design, data-taking strategies, and analysis approaches involves extensive discussion and consensus building. Junior researchers contribute technical expertise and fresh perspectives, while senior scientists provide guidance from experience with previous experiments. The geographic distribution of facilities and funding creates international scientific communities that transcend national boundaries, with researchers traveling regularly between institutions and sharing data and insights across continents. Funding decisions at national and international levels determine which experiments get built and how quickly they can operate. The enormous cost of modern particle physics facilities means careful prioritization of projects based on scientific merit, technical feasibility, and expected impact. When multiple experiments could address similar questions, factors like timescale, cost, and complementarity influence which receive support. The closure of the superconducting Super Collider in the 1990s after a partial construction represented a major setback for U.S. particle physics, redirecting the field toward the LHC at CERN and smaller-scale experiments that could be mounted with available resources. Looking forward, the particle physics community is engaged in planning for the next generation of facilities that might come online in the 2030s and beyond. Proposed projects include a next-generation electron-positron collider that would serve as a Higgs factory, producing millions of Higgs bosons to study their properties with unprecedented precision. The International Linear Collider planned for Japan, the Circular Electron-Positron Collider proposed in China, and the Future Circular Collider studied at CERN all represent possible realizations of this concept, differing in specific technical approach and scale, but sharing the goal of precision Higgs measurements. A subsequent very high-energy hadron collider, possibly reaching 100 TeV collision energy compared to the LHC's 14 TeV, could directly search for new particles at much higher mass scales. Such a machine would probe whether supersymmetric particles exist at masses beyond current reach, whether the Higgs boson is composite with substructure revealed only at higher energies, or whether entirely unexpected phenomena emerge. The technical challenges and costs of such a machine are formidable, requiring advances in superconducting magnet technology and a tunnel perhaps 100 kilometers in circumference. But feasibility studies suggest it could be built with technologies that are either available now or under development. Alternative approaches using muon colliders are also being studied. Muons, being much heavier than electrons, radiate far less energy when accelerated in a circle, allowing circular colliders to reach higher energies than electron colliders of similar size. However, muons decay rapidly, requiring the machine to accelerate and collide them before they disappear. This poses extreme challenges for beam production, cooling, and acceleration, but recent theoretical and experimental progress has renewed interest in this concept. A muon collider reaching multiple TeV collision energy could fit on existing laboratory sites and might offer unique opportunities for precision measurements and new particle searches. Meanwhile, experiments using increasingly intense beams of neutrinos, muons, and other particles probe complementary aspects of fundamental physics. High-intensity neutrino beams enable searches for CP violation in neutrino oscillations and precision measurements of neutrino interaction cross-sections. High-intensity muon beams support charged lepton flavor violation searches and improved muon lifetime measurements. Kaon decay experiments investigate rare processes sensitive to new physics. This program of precision measurements and rare process searches runs in parallel with high-energy collider physics, providing different windows into potential new physics. Progress in instrumentation continually opens new possibilities. Advances in detector technology enable better energy and position resolution, faster timing measurements, and improved particle identification. Silicon sensors with pixels just tens of microns across provide precise tracking of charged particles near collision points. Electromagnetic calorimeters using novel crystals or sampling techniques measure particle energies with percent-level precision. Hadronic calorimeters determine the energy of jets of particles from quark and gluon fragmentation. Muon detectors outside the calorimeters identify the deeply penetrating muons. Sophisticated trigger systems decide in microseconds which events to record from the millions of collisions occurring each second. Each subsystem represents years of development optimizing performance while managing costs and technical constraints. Data analysis has grown increasingly sophisticated with advances in computational power and algorithmic techniques. Machine learning methods now play central roles in particle identification, event reconstruction, and signal background discrimination. Neural networks trained on simulated data learn to recognize subtle patterns distinguishing different particle types or identifying jets initiated by bottom quarks versus those from lighter quarks. These techniques achieve performance beyond traditional methods, improving experimental sensitivity to rare processes and subtle effects. However, physicists remain cautious about relying too heavily on black box algorithms without understanding their systematic behaviors and potential biases. Quantum computing represents an emerging frontier that might eventually impact particle physics. Simulating quantum field theories on quantum computers could potentially provide insights into strongly coupled systems that are difficult to study with classical computers. Quantum algorithms for solving certain types of optimization problems might accelerate data analysis or detector design. However, current quantum computers remain too small and too noisy to tackle realistic particle physics problems, and significant theoretical and experimental development is needed before they can contribute meaningfully. Nonetheless, particle physicists are beginning to explore quantum information science both as a potential tool and as a subject of research in its own right. The relationship between particle physics and cosmology has grown increasingly intertwined. Understanding the early universe requires knowledge of particle physics at high energies, while cosmological observations provide constraints on particle properties and interactions that complement laboratory experiments. The cosmic microwave background encodes information about conditions when the universe was just 380,000 years old, including details about neutrino physics and other particle properties. The abundance of light elements produced in primordial nucleosynthesis depends on weak interaction rates and other particle physics parameters. The large-scale structure of the universe reflects the nature of dark matter and the behavior of neutrinos. This synergy between particle physics and cosmology means progress in one field often illuminates the other. Gravitational wave astronomy has opened yet another window into the universe with implications for fundamental physics. The detection of gravitational waves from merging black holes and neutron stars confirms predictions of general relativity in extreme conditions and provides information about the equation of state of neutron star matter, which depends on nuclear and particle physics at extreme densities. Future gravitational wave detectors might detect signals from the early universe, potentially revealing information about phase transitions or other phenomena when the universe was a tiny fraction of a second old. Some speculative theories predict backgrounds of gravitational waves from cosmic strings or other topological defects that might have formed in the early universe, signals that would provide extraordinary insights into very high-energy physics. The interplay between all these investigations creates a rich and complex landscape, where progress on one front often affects understanding elsewhere. An improved measurement of the Higgs boson's coupling to bottom quarks constrains models that might explain B physics anomalies. a better determination of the strong coupling constant affects both muon G2 calculations and predictions for LHC processes. Neutrino oscillation parameters influence cosmological models of structure formation. Every piece connects to others, forming an intricate web of observations and calculations that must ultimately fit together consistently. Standing at this moment in the early 21st century, particle physics finds itself in a position both frustrating and exciting. The Standard Model, completed with the Higgs boson discovery, works remarkably well. Yet it cannot be the complete story. The gaps and puzzles remain glaring. Why do neutrinos have mass? What is dark matter? What is dark energy? Why does the universe contain matter but not antimatter? How does gravity fit into the quantum framework? Are the forces truly unified at high energy? Is spacetime truly continuous, or does it have fundamental granularity? The anomalies in muon magnetic moment and B meson decays, the discrepancy in the W boson mass, the persistent null results in dark matter searches all reflect this tension between success and incompleteness. Each careful measurement, each improved calculation, each new experimental approach adds information that might eventually resolve these puzzles. Whether the path forward leads through discovering new particles at higher energies, through detecting rare processes that reveal subtle violations of Standard Model principles, through precision measurements that eventually achieve impossible-to-ignore tensions, or through theoretical insights that reorganize understanding in unexpected ways remains to be seen. Perhaps multiple paths converge toward the same deeper truth. What remains certain is that the journey continues. Thousands of physicists worldwide dedicate their careers to these questions, driven by curiosity about how the universe works at its most fundamental level. Students beginning graduate studies today will spend decades pushing the frontiers of knowledge forward, whether by improving measurements, refining calculations, developing new technologies, or conceiving new ways to test nature. Some will experience the thrill of genuine discovery, to that moment when data clearly reveals something unexpected and profound. Others will contribute through the patient accumulation of precision measurements that constrain theory, or through developing tools and techniques that enable future discoveries. The scientific method, that process of careful observation, hypothesis formation, experimental testing, and theoretical refinement, continues its centuries-long record of revealing nature's secrets. Particle physics pushes this method to extraordinary extremes, testing ideas with 15-digit precision, building machines requiring international cooperation and billion-dollar budgets, and grappling with questions at the boundary between physics and philosophy. The field exemplifies both the power and the limitations of human understanding, by showing how far reason and empiricism can reach, while simultaneously revealing how much remains unknown. For those outside the field who watch with interest, particle physics offers glimpses of a universe far stranger and more beautiful than everyday experience suggests. Particles winking in and out of existence, fields permeating all of space, symmetries determining which processes can occur. The quantum dance of probability and possibility underlying all phenomena. These concepts challenge intuition built from macroscopic experience, but represent our best current understanding of physical reality. Whether the muon's excess wobble points toward a new force, whether B mesons reveal glimpses of physics beyond the Standard Model, whether dark matter eventually reveals itself or demands reconceptualizing gravity, the story continues to unfold. Each answer generates new questions, each discovery opens new frontiers, and the quest to understand the fundamental nature of reality proceeds with whatever pace patience, ingenuity, and the structure of nature itself allows.